first of all, hello everyone. Hey. I just want to say thank you so much for inviting me to speak at Lambda World. I'm so happy to be here. There have been some really fascinating talks so far. I've learnt so much. I hope you guys have all learnt stuff too. And I'm hoping that with what I can do here, we've heard so many theoretical talks, and that's just made me so happy because I really like learning about the theory behind what we do. And as functional programmers, I think we should always try and do that. We should always try and learn more about why we use the tools we use and where they come from. And I want to build on that. And I'm hoping that what I can do is consolidate a lot of the stuff that you've heard today. You've probably heard a lot of different terms buzzing around, particularly around category theory. And I'm hoping that this talk will help bring those all together. So I'm going to talk to you about peeling the banana. And my name is Zainab. Just so I can get a show of hands, how many of you know about the kind of banana I'm going to peel? It's called a catamorphism. How many? Okay, that's pretty good. And to be honest, that's kind of what I was expecting. So we've got a little less than half. So yeah, I'm not going to be talking to you about the normal bananas, the ones you have as a snack. I'm sorry. It would have been a lovely topic, but perhaps not quite suited to the conference. What I am going to talk to you about is a paper. It's got the rather friendly title, Functional Programming with Bananas, Lenses, Envelopes, and Barbed Wire. And it's this banana I'll talk about. This paper was introduced in 1991. And that's a long time ago. Right? That's over 25 years ago. And some of you might be wondering, I'm wondering too, why is it that now, 25 years later, I'm talking about this? And so I did some archaeology. And it turns out that in 1991, it's the same year that monads were theorized. And I don't know about you, but ever since I entered functional programming and started learning about things, I've been hearing about monads every day. Everyone has been fascinated and obsessed by these things, and it's almost as though when you begin your rite of passage as a functional programmer, you overcome the hurdle that is monads. So I think one of the reasons is that we've been thinking about lots of other concepts, and so this fascinating concept here, this banana, hasn't really emerged. There are various reasons for that. This is to do with recursion schemes, this paper. And recursion is a difficult concept. Perhaps that's one of the reasons why we haven't dived into it as much as we should. Because I certainly remember when I started doing recursion, started looking at Fibonacci and trying to write a recursive Fibonacci, I got mental stack overflows and a headache and a migraine that lasted far too long. And I'm sure that there will be some of you who had similar experiences. It's not the kind of thing that you can just look at and it clicks. You have to spend a lot of time working out how to build up your recursive functions. But I think there's another reason, and I think that's because the paper itself is steeped very much in category theory. And that's something that you wouldn't have heard about before. For a very long time, it hasn't really been very much involved with functional programming. And it's only really recently that it started to take off. And I don't know if you guys possibly have heard the term category theory at this conference before. Yeah, it's everywhere, right? So this is a great time for us to start learning about all these new things that category theory can bring us. So this is the time for recursion schemes. And I'm hoping that you will learn that today. So I know that most of you still don't know what a recursion scheme is. That's absolutely fine. Don't worry. What we're going to do is we're going to take a look at recursion. In particular, we'll look at recursive data types. And we'll try and generalize recursion on those data types. We'll look at functions called folds, which you might have seen before. And we'll then try and generalize those folds even further. And to do that, we'll enter category theory. And we will use a few of the concepts that you've heard today, some quite basic concepts in category theory, to derive what we need to derive to generalize folds. And one of the things I need to say is don't panic, because when we're dealing with category theory, and in particular with recursion, there'll be some terms which you haven't heard before, such as catamorphism, and a few others. And when you encounter these terms, please try your best to focus on the concept that they represent. Because terms are very useful when you're an expert in the field and you're trying to communicate with other people. But when you're just learning something, really, you should be thinking about what that thing is, not what you call it. You shouldn't have to worry about that too much. So when I do have a new term, I'll try and repeat it and explain it again, so it gets drilled into your heads. If there's something which I've mentioned before, but you've forgotten what it is, you can interrupt me, and I'll repeat it. I'm hoping that by the end of it, we'll have all learned something. So let's start. Recursive data types are things which you've probably encountered before. This is a list. It's one of the first data types we learned to work with. I've taken out the type parameter just to simplify it a bit. So this is just a list of ints. And we know it's recursive because in our cons constructor, we reference list itself in the tail. And so we can think of a recursive data type as something which references itself. And that means that if we want to build it, we're going to build this structure of cons, of cons, of cons. This structure ends in nil. Now this list terminates. I've got a question for you all. If I were to hand you a list in Scala, this is in Scala, would you be confident that the list I handed you terminated? Should we have yes, no? Yes. Yes. Yes, you would. That's correct. And that is because Scala is eager in the way that it evaluates lists. If we were in Haskell, on the other hand, that wouldn't necessarily be the case. You can create an infinite list in Haskell. I want you to assume, for the purpose of this talk, that all the data structures that we deal with are finite. And finite data structures are really cool because it means that we can collapse them. I can confidently take this list and collapse it into a single value. I've written two such functions which do that. This first function, multiply, just multiplies our list of integers. And the second function, length, calculates the length. And you'll notice that these functions call themselves. So in order to multiply all the integers in my list, I need to kind of walk down it and collect what I'm doing. And you'll find that with all recursive data structures, when you want to collapse them onto something, you will need to write a recursive function to do so. But we work with lists all the time. You probably do. And we don't normally write functions like this. This is normally an exercise, right? We'd use something else. And that's known as a fold. How many of you have seen folds before? Good. All right. That's great. It means you're doing the right thing. What we do on a fold is that we essentially say, I'm not going to do my base recursion all the time. I'm going to take out the pattern of my recursion and put that in this function. And the business logic of what I actually want to do, I'm going to separate that out, and I'm going to put that as input functions. So in this case, what we have on fold is that we provide what we want to do in the nil, and we provide what we want to do in the cons. And fold is quite simple. It just says, when we're in nil, call what we want to do on nil, and when we're in cons, repeatedly call fold list, and this is doing our recursion with the functions that we provide. So I can write these two other functions. I can write them in terms of fold, and if you were to write these functions, this is probably how you do them. For multiply, I start with 1, an empty list. I want to get 1 out of it, and I just use a multiply. And for length, I start with 0 because an empty list doesn't have any elements, and as I go, I add 1 to the length. Now these things, these recursive collapses of a data structure, are known as catamorphisms. So a recursive collapse isn't that difficult. We've been doing this a lot, right? You guys use folds. So a catamorphism is just that. It's just taking a recursive data structure and collapsing it into a single value. It's just a complicated term for it. Now, it turns out that we can do the same thing for another data structure. We can take a binary tree, like this, and it looks pretty similar to a list. We've got a case for a leaf, that's the terminal case, and we've got a case for a node, which is a recursive case because we reference tree. So we've got this recursive data structure, and in the same way that we don't need to write recursive functions to operate on it, we can just write a fold function. I've written one for fold tree, and we need to provide what we do in the leaf case and what we do in the node case. And that'll work in a similar way to our fold for our list, right? And so let's say that I wanted to sum all the integers in this binary tree. It's terminated by integers. I could just write fold tree with identity and plus. And if I wanted to count the leaves, something that's pretty similar to a length, I could say at a leaf return me 1, and then just add. So these two data structures and these two fold functions, they're not too different. They both try and do the same thing. Over here, I've got a list, and I'm trying to collapse a list on a single value, so I can build a list catamorphism using fold list. And over here, I've got a tree, and I'm trying to collapse a tree onto a single value. And so we might think, surely it should be fairly easy to take these and just write another function, another fold, that's going to operate on a generic data structure. Maybe I can write a fold that operates on any data structure. But that's quite difficult to do, just looking at this. And the reason being is that list and tree have different shapes. Over here, I've got an integer, and over here, I've got a tree. And the nil case is different as well. And I can have other recursive data structures, and they can have more than 2 cases. If you've ever seen an expression tree, that will have several different cases. And so it is very difficult to produce that general data structure, especially just by looking at the code. And we could look at this and scratch our heads. Maybe we could even dive into shapeless and generic programming, but that probably wouldn't be the best way of going about it. So instead, we're going to use something else. We're going to use category theory. Okay. Yes. Okay, I'm sure that you guys have probably seen this diagram at some point today. But I think that I should just go over it again anyway. Just let's consolidate. So there are 2 things in category theory. There are objects and there are morphisms, also termed arrows. This A, B, and C, these are objects. And these F and G, these are morphisms. Now, in the category that we're working with, we're working in Scala, so we've got functions and types. So objects are types, and this F and G, those are just functions. There are 2 rules. One is that for every object, we can write this identity, which is specific to the object, and that doesn't do anything. So that means that I can do ID A and then compose with F, and that's just the same as just doing F and ID B, which is just the same as F. So ID doesn't do anything. And we've also got this associative composition rule, which is just that F and G, then H, is F and G, then H. Oh, and of course we can compose F and G into a single arrow, FG. Okay, you guys okay with this diagram? Yeah, we've seen it a few times. Okay. Let's first state what we're trying to do. I want to take a general recursive data type, which I'm going to call R, and I want to collapse it onto a single value, which I'm going to call A. So previously we saw collapsing a list into an int by summing all the elements. Just imagine R is your list, A is your int. And so what we want to do is write a function. It's going to be a catamorphism, so I'm going to call it cata, that goes from R to A. And if we're using category theory to do this, the only thing we can do in category theory is compose, which means that if I do want this function, I'm going to need to build it up from other things. I don't know what those things are quite yet. But this is what we're trying to get to. But the first thing I'm going to do is not in fact do that. I'm going to do something which is slightly tricky. I'm going to take my list and I'm going to make it higher-kinded. I'm pulling the recursive part out. Over here is where I used to reference my tail. I'm pulling that out and putting it as a type parameter. And you're probably thinking, why would you want to do this? This is crazy, isn't it? I mean, this thing isn't a list anymore. I could put anything in here. I could put, for example, some string, foo, and this isn't a list. On the other hand, I could put it inside itself. I could call this recursively. And that looks kind of like the list that I started with. But we need to define what that means. These things, they look a bit the same. When I say they look a bit the same, what I mean is that we can go from one to the other and back without losing any information. So for example, I can go from a list f of a list to a list. I can write a function that does that, and that just converts the constructors. Instead of nil f, I go to nil. Instead of cons f, I go to cons. And I can also write a function that goes from a list to a list f of a list. I can go back. And similarly, in the case of nil, I go to nil f. For cons, I go to cons f. And there's a special term for this in category theory. You may have heard it before today. It's known as an isomorphism. It essentially means that we can take one type, R, and another type, FR, and we can convert between them. We can convert back and forth, and we don't lose any information. That's just what I've written. I've said, imagine this is our list, and this is our list F. Right? I can go, if I start with my list, I can go out and then in, and that's just the same as identity. And if I start with my list F, I can go in and then out, and that's just the same as identity. And this is really nice. It feels kind of useless, though. Why would we invent some other representation which does exactly the same thing as our original one? Why would we bother doing that? But there's a really important reason, and that's to do with functors. How many of you know what a functor is? How many of you think? Okay, good, cool. That means you're all following along. So a functor is something which takes an object A and takes it into a type, or rather takes a type A into another type, FA, and takes functions from A to B into functions from FA to FB. And we might draw it like this. We might say we've got A and B, some function F, and we go from FA to FB via mapf. And this is how we implement it in Scala. We say this thing here, this F is the thing which goes from A to FA, and we have a map function which goes from FA to FB, or takes a function from A to B and goes to a function from FA to FB. And it turns out that I can implement this for my list F. I can't implement it quite in the same way for list, but I can do it for list F. So I can say that I'm going to take a function from A to B and map it into a function from list F of A to list F of B. In the case of nil, I can't do anything. And in the case of cons, I'm going to apply it to my tail, or my value A. And you might think, why would you possibly want to do that? What else do functors give us? And the answer is that functors give us a really interesting construct called an F-algebra. And this is actually just a function from our functor of A to A. Now that's not too confusing. It's got a confusing name, but really it's just a function. And the way that I define it in Scala is via a function. I say this F-algebra is just a type alias to some F of A to A. I've omitted the fact that F really ought to have a functor instance here. And you've seen these before. I've already shown you one earlier. In fact, the function in that we wrote here is an F-algebra from list F to list. So we wrote a function that went from list F of list to list. I could just as well write another one, and so I'm going to randomly pick one out of a hat. This doesn't look suspicious at all, right? I've just come up with it. Called multiply algebra. And that goes from a list F of int to int. And in the case of nil, I'm going to go to 1. And in the case of head and some value I in my tail position, I'm going to multiply h and I. And we've not done too much, but we've done everything we actually need to do to solve our problem. Let me go through this. So what we were looking for is this function from R to A, which we called cata. We want to go from our recursive type to a single value. We want to collapse it. And we came up with this other bizarre functor representation, this list F, and we found that we could convert back and forth. We wrote conversion functions in and out, and those were isomorphic. And the next thing that we said is that, okay, list F is a functor, which means that I can map. And we also said, well, I can write these other things called algebras, which go from FA to A, from my list F of, in our case, we wrote a multiply algebra, right? List F of int to int. And so, because category theory is all about composition, we can now compose all of these. I can say that if I do have this function cata, I can just as easily have another function, map cata, via my functor, right? I can have that function, and I've got an isomorphism between these two, and I can write an algebra. Now, looking at this diagram, can any of you see a way of composing everything we've done such that we can get this kata. Can anyone see a path, possibly, through this picture? Okay. Should I give you a moment? Are we ready? Are we ready? Okay. Let's go. I've drawn it out for you. It's this one. So we can go here, take our function out, then map kata, and then apply alg, and that's the same as our catamorphism that we wanted in the first place. We've got there. That wasn't too hard. So we just compose these, and we can do this in Scala code. And this is what it looks like. It's not quite as neat as it would be in Haskell. I'm sorry about that. It's just one of the problems when we're working with brackets. But essentially, it does the same thing. We say, OK, I'm providing an... well, let's go through this slowly. So given I've got a general recursive data type R, and I've got an algebra from FA to A, where F is my functor, and I've got out, which is my isomorphism, from R to FR, then I can create a function that takes any recursive data type, this recursive data type R, and collapses it into a single value. And the way I do that is that I operate out, and then I operate my functor map on kata itself, and then I call my algebra. So we're just doing the same thing that we saw over here. We're just writing it in Scala. And so let's say that I now wanted to write a function that multiplied my list to an int. I could write that in terms of this, because I could call kata using my multiply algebra that I wrote earlier, and using this out isomorphism that I defined. And that's really amazing. I think we need to just take a pause here and just congratulate ourselves on what we've achieved. We've managed to create a generic fold. This is going to work on any data structure that we choose. All we need to do is define a few things for it, and we've essentially managed to do what we couldn't do earlier. If you looked at the first picture, when we were comparing a list and a tree, and we were trying really, really hard, weren't we, to try and figure out what we could do, I don't think we could have got here via any other path than looking at the different concepts in category theory that we've seen. And so I think that's really amazing. And maybe we could stop here. Maybe I should just end this talk, and that should be it. But in fact, we can do more. We can keep going. What about building stuff? Have any of you tried to build a list from a single value? Over here, what I've got is that I've written a function called range, and what that does is that it takes in an integer, and it builds a list of integers going up to that. So let's say that I wanted to build a list from 1 to 3, I could enter 3 and it would go 1, 2, 3. It would build me this list. Now there is a technical term for this thing, this building. It's called an anamorphism. But an anamorphism is just generalized building, opposite of generalized collapsed. Well, not even generalized, in fact. Any kind of building, you can call it as an anamorphism. And so maybe we could try and get this. This is just the diagram we wrote before. Maybe it would be possible to get an anamorphism out of this. An anamorphism goes from a type A to my recursive data type. And is that possible? Is that possible? No, it's not quite. On the other hand, let's say that I took this arrow and I reversed it. Let's say that instead of producing an algebra that went from FA to A, I produced a co-algebra. I went from A to FA. Then in fact, I can produce a path here. And I can use, operate my co-algebra, then map Ana, and then operate in. And that's just the same as my anamorphism. So I can use pretty much almost the same things that I've used so far to derive my generalized fold, I can use to derive a generalized unfold. And this is what it looks like in Scala. Again, this co-algebra is just a type alias. It just goes from A to F of A, where F is a functor. And I can write an anamorphism like this. And so if I wanted to write a coalgebra for range, it would look pretty similar to what I wrote before the actual range function. I'm just saying that in the case of when n is 0, I have a cons of n and n minus 1. And if n is equal to 0, then I'm going to have nil. And so I can produce my range function from this anamorphism. And we could stop there as well, but I think that we can go a little bit further. What if I just have recursion itself? What if I don't have a data structure? Let's say that I have this factorial function. I was plagued with factorials when I first started recursion. Factorials and Fibonacci's, those two things, the most difficult things you can do in functional programming, I think. This is called a hylomorphism. And it's pretty interesting because, in fact, the call tree of a factorial function can be modeled as a data structure. So let's say that I wanted to model this. It goes a function from int to int. Let's say I wanted to model this. I can actually try and put together everything I've done so far. That's all we've been doing, right? We've just been adding to this diagram. Let's try and put together everything we've done so far to get this function. So we want to go from sum A to sum B, and we know that we're going there via some recursive structure. Let's say that I write a coalgebra, and I write an algebra. Is there a possible path? There are probably quite a few possible paths, aren't there, looking at this diagram, that I can use. And in fact, I'm going to pick one of them. I'm going to pick this one. I don't know if you guys, can you guys see the green? I hope you can. If we apply our coalgebra, then we apply map of Hylo, and then we apply algebra again. The interesting thing about this path is that I completely bypass my recursive data structure. So what I've produced is a function, Hylo, which doesn't even use a recursive data structure necessarily. What it does require is a coalgebra and an algebra. And factorial is kind of interesting because I can actually build it up using the things that I've shown you already. I can build it using the range coalgebra that I showed you earlier and the multiply algebra. And when you think about it, that's pretty intuitive, isn't it? Because when we take a factorial, what we're doing is we are mentally producing a range of numbers from our starting number down to 1, and then we're multiplying them. And so this is really interesting because by modeling a recursive function in this way, we can intuitively create this recursive data structure without actually having to do it in the code or at runtime at all. So this thing really should have the same performance as my initial one. But there is an elephant in the room here, something that I have not told you, which is that in doing this, we have introduced quite a bit of boilerplate, haven't we? Because we said, well, not only do I have my initial recursive data structure, I've got this other one, the one with the functor, and I've had to write an isomorphism for these two. So I've had to write a function that goes in and out for those. And I think for us as functional programmers, we always want to reduce our boilerplate, don't we? And so hopefully there's a possible way of doing this, because otherwise everything I've shown you it's not going to be too useful. And what we're really looking for is a function. Let's say that we start with our listf, right? Let's say we start with our type, which is our higher kinded data structure with a functor. What we're really looking for is to be able to model this using something else, some foo, by which we can easily write a function that's an isomorphism. So we can easily write an in that goes from listf of foo to foo, and easily write an out that goes from foo to listf of foo. And it turns out that there is something that does this, and it does look a bit scary at first. It's called fix. And I think that it looks kind of bizarre. Because essentially what it does is it takes this type, which is higher kinded, well, it actually takes an f of a fix of f and produces a fix of f. And it looks strange, but in fact it works. We can write our isomorphisms. We can write in, going from a listf of fix of listf to a fix of listf, and that's just the constructor. And we can write out, that goes from a fix of listf to a listf of a fix of listf, and that's just calling unfix. That's just doing the unapply. And this is a really interesting concept, because essentially what we're saying is that we're coming up with a new definition of what a recursive data structure is. Because instead of saying that a recursive data structure is something which references itself now, instead of it being my initial list, what I can actually say now is that for any functor, I can take that functor and produce a recursive data structure from it by taking the fixed point. I can essentially repeatedly apply that functor to itself using fix like this, and that will give me a recursive data structure. And I really encourage you to play around with this if you haven't done so already. Take functors which you're familiar with already. Why don't you take option, for example, and repeatedly apply it like this and see what kind of structure you get. It's really interesting when you do so. And you can do so with other things as well. You can do so with either, and you'll get a different structure. So we've actually come a long way in a short space of time. We've tried to derive some general recursion schemes. We've tried to derive a general way of recursing over a data structure, and we have, using category theory. And I think that that's amazing. I hope that you guys also think that category theory is really cool. I think that that's one of the takeaways of this entire conference, that is something that we should be looking at. By the way, it's not as though any of the speakers beforehand all met up secretly and decided that this is what we're going to do. It wasn't some kind of a coup. It's completely natural that category theory has entered into functional programming at this time. And I think that it's really amazing that it's done so, and it means that we can explore all these new concepts. I hope that you guys have a bit more familiarity with recursion and with recursion schemes, and also with fixed points as well. So, in case you can't see, I ought to say that there are libraries that help you do this. So some of the things that we've done so far, we wrote catamorphisms, anamorphisms, hylomorphisms. These all exist and many more. There's a library called Matryoshka in Scala, which I recommend you to check out. There's one called Recursion Schemes in Haskell by the wonderful Erik Meijer. And there's a port of that in Idris as well, which I haven't had a look at yet, but I would definitely recommend it. And if you do want to learn more, I think that I've given you enough knowledge that you can probably take this and go and read the original paper, which is really cool, and it goes into this in far more detail. Of course, you can't get to talk with category theory without referencing Bartosz. Thank you so much. I don't think that I could have even given this talk without all of his wonderful posts. I've put a particular one on F-Algebras here, but I would just recommend you to read everything by him. There's a really interesting paper by Philip Wadler, in fact, called Recursive Types for Free, which goes into fixed points in far more detail. And so if you're more interested in the relationship between fixed points and recursive data structures, then that's a good one to look at. And it turns out that I'm referencing another speaker here, which is Jeremy Gibbons, who's also done a lot of stuff on recursion schemes, in particular how you can apply them to object-oriented patterns. So I think his work is really cool.